Hey guys, we are on slide 14 of chapter 5, talking about thermochemistry. I'm going to go back and forth between the PowerPoint and the whiteboard today. Slide 14 talks about the heating curve. Essentially, the idea of the heating curve, it's going to be a graph that we're going to build based off of what happens when we heat up a substance. So let's just say, as an example, if I take a piece of ice out of the freezer, and let's say the temperature in the freezer is negative 20 degrees Celsius. Okay. Now again, in a freezer, the temperature is always going to be below the freezing point of water, but you can control the settings of the freezer. So my initial temperature of the ice is negative 20. I take it out of the freezer, I put it into a pot, I turn on the heat, and then basically we want to make a graph of what happens. So normally in class I would ask the students what happens when I start heating up a piece of ice. The answer is normally that the ice starts to melt. Okay, that is not the answer that I'm looking for. I kind of expect it, usually make a joke out of it, but essentially the ice, if the ice is at negative 20 degrees Celsius, it is not ready to melt. You have to warm the ice up from negative 20 up to 0 degrees Celsius, which is known as the melting point of water. You have to heat it up to that temperature before melting occurs. Okay. Now, in this scenario, we are making some assumptions, like the fact that as we heat the ice up, we're going to assume the entire piece of ice is heating up evenly. If you put a piece of ice in a pot, of course, the very bottom layer is going to heat up a lot faster than the rest of it. So you will pretty quickly see some melting occurring. But even that bottom part has to be heated up to 0 before it melts. Okay, so we're going to graph. Again, I can start anywhere, but if we just say we're going to start at negative 20 degrees Celsius. So on my graph, you notice I have temperature on the y-axis. I have as I add heat, it moves me to the right on my x-axis. So that says heat added. So when I put it on the pot, as I add heat, it's going to shift me to the right. I'm starting at negative 20 degrees Celsius. So from that point, if I add heat, the temperature is going to go up. As I move to the right, that's going to create a diagonal line. It will continue that as I add heat, the temperature will go up until I get up to 0 degrees Celsius. When I get to 0 degrees Celsius, that's going to be the point at which melting begins. Now, we have to think about what's the graph going to look like when melting happens. Well, a lot of students have trouble with the idea of melting, but when I go to boiling, everybody's pretty clear that if I take a pot of water and put it on the stove and warm up a pot of water, when it gets up to 100, the water starts boiling. And let's just say I leave the burner on the stove on high, it boils for 45 minutes. If I ask the students what temperature will the water be at the end of 45 minutes, everybody always knows it'll be 100 degrees Celsius, because while you're boiling water, the temperature will stay 100 the whole time. Okay? Well, freezing of water or melting of water is the same idea. I'm just using 0 degrees instead of 100. So during the melting process, the temperature of the ice or water, as it's converting, the temperature of that ice-water mixture will stay at 0 until the melting has completed. Okay, so once the piece of ice is completely melted, that's the point when the temperature can start to go up again. So what that does, it creates a horizontal line on my graph where during the melting process, there is no increase in temperature. Okay, so I can label my segments here. The first segment on the diagonal is going to be warming the ice. The second segment is going to be melting the ice. And then basically that will happen. I'll have to add a certain amount of heat, because melting ice is an endothermic process. You have to add heat to make molecules start moving to where it breaks out of the crystal structure of the ice and gets the molecules moving freely. So you have to increase the kinetic energy of the particles. So when I get to the end of that, that'd be the point where the last little bit of ice breaks free of its structure. I have pure liquid water. At that point, if I keep heating, So I just leave the stove on, more heat enters into the sample, then the temperature of the liquid water, which when I finish melting is still at 0, but I can start warming the water up. I can warm up the liquid water in the liquid state all the way up to 100 degrees Celsius if I want to. So I'm going to draw another diagonal. As I add heat, my temperature goes up, so I get another diagonal that's going to take me up to about 100 degrees Celsius. So let's just say that's my 100 degrees Celsius. And at that point, another phase change is going to occur. At 100 degrees Celsius, the liquid water is going to start to boil. So I'm going to get another horizontal section of the graph representing the boiling. And then once it's at the end of that segment, that's where I've converted all the liquid water. Here it's all liquid water at 100 degrees. As I move across, I'm converting more and more of it into gas. When I get to the end, that's where the last drop of water converts into the gaseous form. And then finally, if I heat it up some more, the temperature of the water vapor or gas can go up again. So that's going to create another diagonal section. So this section is going to be the warming of the gas or the water vapor. This section is going to be the boiling of the water in liquid form. And this is going to be warming the liquid. So this graph is called the heating curve. It is specific to water. Now, why is it specific to water? Well, almost every substance, as we heat it, will go through a solid, liquid, and gas state. But the reason it's specific to water is that the phase changes are equal to the temperature at which the freezing point and the boiling point of water happen. Okay, so 0 degrees and 100 degrees, that is the freezing point and boiling point of water. If I graphed the heating curve of another substance, most substances, the graph will look just like this, but it'll have different freezing point and boiling point. Okay, now you do have a few rare substances like carbon dioxide. If you go to the store, you can get dry ice is solid carbon dioxide. If you heat it up, the dry ice will convert straight from the solid form into the gaseous form through sublimation. So that process, like that graph, if it only goes straight from the solid to the gas, instead of having 5 segments like this one does, it would only have 3. It'd have the warming of the solid, it'd have the sublimation as horizontal, and then it'd have warming the gas. Okay, so there can be variations, but most substances will go through these 5 steps. Now, what's really important about this, of course, is to understand where each step occurs, at what point in the process you are, but each step represents a separate calculation that has to be done. Okay, so so this is my heating curve label. Now, if I'm going up from low temperature to high temperature, or moving from left to right, that's going to be heating the sample up. That's when I'm adding heat to the sample. This curve can be turned around, where if I start cooling it down, I would move from the high end of the graph down to the low end. You can draw it as a separate graph and call it a cooling curve, but to me it's the same idea. It just depends on if you're moving up or moving down. The calculations are exactly the same. Some of the labeling might change. Instead of putting boiling, if I'm coming down, that would be taking the gas and condensing it into the liquid form. And then if I'm going down, instead of melting, it'd be freezing. But the process is the same. Okay, so calculation-wise, the warming of the ice, I usually call that Q1. Melting the ice is Q2. Warming the liquid is Q3. Boiling the water is Q4. And warming the gas is Q5. Remember, previous calculations we had Q is the amount of heat that is required to achieve a process. So I've got Q1, Q2, Q3, Q4, and Q5. Now, of these 5 calculations, On the previous video, I've already set up how to do them. Q1, Q3, and Q5 are going to be, I'm heating up a sample within one phase. Okay, we did a problem a little while ago where we had liquid water and we were warming it up from like 22 degrees to 85 degrees or something like that. If you're just moving up a diagonal, you do MC delta T, where you should know the mass of the sample, you should know the specific heat of whatever substance it is, and it is specific to the physical state. So liquid water is 4.184 joules per gram degree Celsius, and then delta T would be the change in temperature. Okay, so for Q1, Q3, and Q5, they're all going to set up that way. Q2 and Q4 are going to relate to the amount of heat involved in the phase change. Okay, if I want to melt 1 mole of ice, we looked up in the appendix earlier, it was 6.008 kilojoules per mole. So if I'm melting 1 mole of ice, then that's how much heat it takes. So if I just multiply the amount of sample in moles times the heat of fusion in kilojoules per mole, that's going to give me the kilojoules that it takes. So that's Q2. Q4 is the same thing, but it's vaporization instead of melting. So in the appendix, there's another value for the heat of vaporization, 40.67 kilojoules per mole. You don't need to memorize those numbers, but you do need to know where they are. They're in Appendix B of your textbook. And you're welcome, if you're doing this class online with the formula sheet that you should have when you take the test, you can write those numbers down if you want to. You want to have all that stuff accessible when you do your problems. Okay, so I'm taking long enough that I won't be able to finish the next problem on this video, so I'm going to cut off the video and we'll work an example of these calculations in the next video.